Alright, let's take another look at this rabbit. I'm just going to refresh the problem, what we've done so far. We were given the path in an XY plane that the rabbit runs at, and it's a function of time. The X coordinate's a function of time, and so is the Y coordinate. So at any given time t, we can evaluate it and figure out the position vector r. And we did that. And we found that t is equal to 15 seconds. It is 66 over to the right, call that 66, and negative 57 down. Something like this. We'll draw a better sketch of this, the velocity, and the acceleration all together in just a moment. But what we did, if you remember, was then take the time derivatives of these. And we ended up with a negative 0.62t plus 7.2. That was just for the x. That is the velocity in the x direction, or dx dt. If we want dy dt, we take the derivative of the y as a function of t function, and we get a 0.44 t minus 9.1. Alright, so this is in meters, and this is all in meters per second. And meters per second. Oh, and it's got meters in there already. Okay, we can then evaluate that just like we did the position at some time, let's say 15 seconds. We're continuing the problem, and we get a velocity vector now, where we take the x component and put it next to the I, and we take a y component and put it next to the j. If you have a z component, you would put it next to the k. What we got in our previous problem is, if you don't remember, go take a look, is negative 2.1 meters per second in the I direction, plus a negative 2.5 meters per second in the j direction. Okay, we're going to hold on to the, oh, no, not this one. Let's hold on to that. I want to draw that vector for you too. So we're going to sketch the position, the vector, and then the acceleration. So what do you think we do to get the acceleration? We take the derivative again. Let's take another time derivative. So if I wanted to look at each component separately, take this v sub x, I want the time derivative of v sub x. That would give me just a negative 0.62. Oh, no. And it would be meters per second squared. So that's the acceleration in the x direction. If I did the acceleration in the y direction, we'd have the derivative of velocity in the y direction. And don't forget, the acceleration is also equal to the second derivative of position with respect to time. So you can't take two in a row. I don't know a trick to take two without doing them sequentially. So if you do, please let me know. But we get, by taking the derivative of this one, just the 44 right there, 0.44. Alright, let's put that into a vector now. So the acceleration vector, it's still a function of time, even though it's all constants. It did come from a function of time. Time is passing, right? But these values are not changing. I get a negative 0.62 meters per second squared in the I, and a positive 0.44 meters per second squared in the j direction. Alright, we got it. If I wanted to figure out the magnitude of this, we could take the square root of those components. So 0.62 squared. Take the square root of the components added up after you square them. And we can get a value of 0.76 meters per second squared. So this is how long the vector is. If I wanted the angle, then we could do the tangent inverse of the y component over the x component. In this case it's 0.62, it was a negative, but I'll show you to make sense of the direction and by actually graphing it. Leaves less room for error in my opinion. And we can get an angle of negative 35 degrees. Okay, negative 35. Okay, let's graph this thing. Let me see if I can do something clever. That didn't work. Alright, we'll just rewrite it. So the position's at 66, negative 57. That's what I was looking for. The position is at, oh man, see I'm bad at memorization, 66, 57. And that's in the I direction, this is in the J direction, and this is all in meters. Alright, so let's go ahead and graph that. And let me write down the velocity actually. The velocity at 15. Save some space, is a minus 2.1 in the I direction and a minus 2.5. Alright, so we need those two, and go ahead and copy this down. Our acceleration vector was negative 0.62 in the I direction and 0.44 in the J direction. That whole thing is in meters per second squared. This whole vector for velocity would be in meters per second. Alright, now I have those where in a position where I can graph. Let's just do a simple XY coordinate system. And let's plot the position first. First of all, let me plot the position, and then if you wanted to plot the path, you just plot a bunch of different time intervals and you can find it. So I'll do a rough sketch of the path, but know that you can just plug in different times t and then plot the points. So let's call this maybe 10, 20, 30, 40, 50, 60, 10, 20, 40, 50, 10, 20, 30, 40, 50, 60. I think that'll get us there. The point is at, I'm looking at this one, 66 over. So a little bit more than 60, a little bit less than 70, and then almost to 60. So something like this. We can get our point. This is its location. If I wanted to plot a bunch of different points, what we would see as time evolves, it comes through 50 around here, and then comes back up something like this. And you can get the direction, because that is the direction time goes. As time gets bigger, you start plotting points in this direction. So you know that's the direction of motion, or that's the direction it's going along the path. Clean this up a little bit. Okay. There we go. A little bit better. Let's plot the velocity. Let's pick a color. Let's pick blue. Velocity is in blue. We have this vector right here. It's going 2 over and, or negative 2 to the left. Sorry, it's going 2 to the left and 2 down. It's not very much. Just something like this. And the resultant velocity vector, well, it better be tangent to that path, right? If it's not, check your work. It must be tangent to the path. And the acceleration, however, is almost never tangent to the path. So our acceleration, I'm going to do in orange. I'm looking at this one right now. The vector should be smaller, but we're on a different scale actually, right? This is in x in meters. This is in y in meters, so you can, as long as they are to scale, you can draw it as big as you want. I could have drawn, for instance, this velocity vector as long as I drew them to scale, meaning this one was to a scale of 2.1, while the one that goes down is on a scale of 2.5 or a little bit longer. You see we get the same direction of the vector, and it's still tangent to the path. For the acceleration, let's choose orange. We have a negative 62, so just something going in this direction, in the negative I direction. That's that one. And then a positive 44. So not quite as much as the 62. It's pretty close to scale. And if we added those two vectors together, we would get our acceleration vector. So it's our acceleration, and this is our velocity. Makes perfect sense, actually. So graphing is a very powerful tool. What we should be seeing when we look at this is, one, that the velocity is tangent to the path. 2, it should be, it's coming around this corner like this, right? So it better be pointed in that down to the third quadrant direction, right? It better be going in this direction right here. So you can get the direction from the graph. What else? That came just from the vector too. I didn't have to plot all these points actually. What else? The acceleration. We're going to learn all about accelerations, and this one happens to have a change in direction. As this particle is coming around the corner, something has to cause it to accelerate in the direction of the turn. And then once you're out of the turn, nothing's accelerating anymore. So there's two types of acceleration, or there's two different things that can cause acceleration. One would be a change in speed, and the second would be a change in direction. Okay, we could check our angles. Everything looks good. This angle right here was the angle we just found for the acceleration. If you notice, we got a negative 35 back. Well, that's because the negative 35, if we would have measured from here, would have been a positive 145 degrees. So this was made by looking at components, right? We had the acceleration on the y and the acceleration on the x. Therefore, this is the angle that we're going to get back. We have to make sense of that angle. If I wanted to report the acceleration, I would probably want to give that angle. And if I had to take the acceleration, let's say we were given the magnitude and the angle, then I would want to break up the components using the angle from the x-axis, this one right here. If I did that, then we get the acceleration in the x direction is equal to the magnitude of the acceleration times the cosine of theta, and we don't have to worry about what sign to give it. Same thing for y, except it's the sine of theta. Alright, next we will look at projectile motion.